Thank you so much for the invitation and for having me here. Yeah, I would like to talk about a couple of things related on online learning, and it's two separate arguments. There's online learning as a common background, but the first is online parametric learning. It's a very nice, actually it's an old result. I would like you guys to know and possibly to revamp it. We have been using this algorithm in the last year, pretty much, with these co-authors, Francesco Labone and Rocco Da Rosa, and found it very interesting with very nice applications, for instance, in online activity recognition in videos. So this is about online randomized classification in metric spaces. Well, we can do it. We can work in metric spaces. It's not a big deal. You can think of Euclidean space if you don't like to work in metric spaces, but the algorithm is general enough. You can deal with that. And it's about online learning, so we don't make an assumption about the way the data source is generating the data. So we are facing a completely arbitrary deterministic data source, and the data source is giving us. Is there here? Okay. It's giving us data points and labels, and we assume labels are binary when doing classification. And this is the online protocol. The learner is going to get the instance at each time step, and it's going to output a randomized prediction. And P sub t is the probability that with which will be assigned to label 1. And then we observe, the learner will observe the true class label, and will pay a loss whether the classification is incorrect. And the probability of the loss can be written as just the absolute loss, because the labels are binary, between the probability of outputting prediction 1 and the actual label. So this absolute loss is just the probability that the learner makes a mistake at time t, when the probability of predicting 1 for the learner is p sub t. So this goes on, and we are interested in controlling the expected number of mistakes, which is the total absolute loss over any arbitrary deterministic source. Okay, so this is a problem, and this time we are interested in, this is a very general problem as we study with different losses, not only the absolute loss, which corresponds to randomized classification, but also with very many different losses. And in this particular case, we are interested in using as a reference class, and I'm going to tell you what it is, the class of all Lipschitz functions. So we are, okay, you know the definition of the Lipschitz function, and we are interested in competing against Lipschitz functions that are used as probabilities for predicting the same sequence. So some Lipschitz, let me introduce the definition of regret now. So given some data source, some deterministic data source of points and labels, we computed the expected regret, which is the difference between the cumulative expected number of mistakes of the learner, which follows the protocol I just gave you here, and as our outputting prediction PT. So this is, I'm using this in order to denote the absolute loss. So this is the expected number of mistakes of the learner, which is observed in the sequence, and this is competing against the best Lipschitz function over the same sequence of data. So we're looking at the smallest Lipschitz function, the infimum over all Lipschitz functions of f of the expected number of mistakes made by the fixed Lipschitz function of the same sequence of data. So again, the data is completely deterministic. So I'm not assuming there is a specific Bayes optimal classifier for the sequence, which is corresponds to a certain Lipschitz function. I'm just taking an arbitrary sequence of data and I'm competing against the class of Lipschitz functions. Okay, this looks like a tough problem, and it's a classical problem of non-parametric statistics that's been well studied for years. So in particular, you can study this problem in a metric space, in metric spaces, and the key parameter here is the doubling dimension, which is extends the Euclidean dimension. And essentially, we say the metric space doubling dimension D if you can pack 1 over epsilon to the D balls value epsilon in the space. So this is a measure of the complexity of the space in terms of the number of balls that you can fit with a certain radius in the space. Okay, we're talking about totally bounded metric space. and we assume that this number is finite. Okay? So if the source is actually stochastic, and there's some Lipschitz function, which is the base optimal classifier for that source, then we know that, for instance, by running nearest neighbor with an appropriately chosen time-dependent parameter k, okay, under some assumptions and maybe additional assumptions, we can learn the expected mistake rate of the, I'm looking at the right picture, yes, of the nearest neighbor classifier, yes, with respect to the base optimal classifier is going to grow at this rate. You're actually probably used to see this divided by t, but I'm looking at in the online learning is typically the regret grows with time. You don't divide by time, so you see a growing sequence, and you're interested in a sublinear growth. Okay. So, and the question here, so this is a known result for many non-parametric algorithms achieve this. For instance, I mentioned nearest neighbor, and we're interested in matching this rate using a randomized strategy in a completely non-stochastic setting. So the algorithm I'm suggesting you is this ball covering approach by Azan and Megiddo. And this is a very versatile and simple way of approaching the problem. So so it's a non-parametric problem. So you're covering your space with balls that are half overlapping, meaning that the center of the ball doesn't enter any one of the adjacent balls, but the ball can partially overlap. And each ball has a local classifier sitting in it. Which classifier would you like to pick? Well, it depends on your problem. And for making a prediction, you just work with nearest neighbor. So you predict any new point with the closest classifier, with the classifier sitting in the closest ball. And for updating, you look at all the points that you saw previously. The problem is sequential, and that they fell into the ball. And clearly, because you want to converge somewhere. And the problem is, and you're looking at a non-parametric class of functions, you want the radius, the radii of each of the balls shrink with time in order to cover better and better space. Okay, so how are we going to analyze this algorithm? Okay, here's the algorithm spelled out. So we create a default cover containing a single ball with a default local classifier, and we get instances from the stream, from the data sequence. We compute the closest center, which I denote with stars. So this is the center of the ball closest to xt, and we predict the level of xt using the local classifier sitting at that center. Then we observe the true-class label, and well, we know whether we made a mistake or not. And if xt is not contained in the ball center, in the closest ball, then we have a new ball with that point as a new center. So this set of balls grows, and the radii shrink, so you're going to get the covering. And then you shrink the radii of the balls according to this specific law, which is going to get you the right rate. So we use majority voters and local classifiers, but you can use many different classifiers. You can use linear classifiers, if you want to lift this up to a more general setup. We just use majority voters in this case. So the analysis is like 2 pages. So that's beautiful. I love it. So you fix any Lipschitz function you want to compete against it. This is the Lipschitz constant for that function. And then you look. So basically, this is the regret, and you split the regret contribution among all the balls. So you look at some point of time, there's going to be a number of balls sitting around, and you look at the number of mistakes that each ball made. All right. So this is the expected number of mistakes made by the classifiers sitting in the ball. That classifier example at time t. Okay, so we split all the examples t that were given to a certain center, x sub s, and we sum over all centers, x sub s over c. C is the cover at the end. So we look at the final cover, and we're looking, okay, who's responsible for these mistakes, who's responsible for these mistakes, so on and so forth. And then we just make this split. So we add and subtract ps opt. Ps opt is the best prediction which is going to be, it's a binary problem, so this is going to be either 0 or 1, is the best prediction for all the examples that fell in a certain ball. It's just a majority. Okay? So, right, since this is the best prediction, it's going to be smaller than the number of mistakes made by the best, by the center of the ball. So we can do this majorization, and then we can just apply, okay, this is just by Lipschitz, we can bound this by the Lipschitz constant times the radius of the ball, and this we can use online analysis. This is a problem of competing with the best of two experts on individual Simpson points. So we use the classical results from experts in order to bound this by the square root of the number of examples that fell in the ball. I'm omitting constants here for clarity. So just by using Jensen, we can now introduce the sum over the number of the number of elements in the cover. And since we know the shrink rate of this thing, and the shrink rate is global, we can just upper bound this by this sum, which is upper bounded by the integral. And again, I'm omitting constants there. Okay? Now we can just say, all right. So since we picked this, and we know that because D is the dimension of the metric space in which we do the classification, the Pecky number bounds, which is the definition essentially of the metric dimension for the space, will get me an upper bound on the numbers of balls I can fit in that space. Okay? I cannot fit too many balls of a certain radius, so the size of the cover can be almost as much. Now by making the calculations, I get exactly the right monoparametric rate, which will depend on these two constants. This is the Lipschitz constants of the function I'm competing against, and this is the constant that relates to the cover, the metric space I'm dealing with. Okay? So nice. So now I can say that for the final theorem is the following: for any deterministic source, I can make a randomized classification with an expected number of mistakes that is simultaneously good against all Lipschitz functions, all Lipschitz randomized classifiers. This is an oracle inequality. So the algorithm is completely oblivious to the Lipschitz constant of the function is actually looking at. So it is competing simultaneously uniformly over the entire set of Lipschitz functions, and it gets the right rate. And this is the kind of trade-off. So you have a trade-off between the fit of the parametric function of the Lipschitz functions that you're competing against, and the complexity of the Lipschitz constant of the functions. Okay. So right, you need to know, in order to tune your epsilon, the rate at which the balls shrink, you need to know the metric dimension of the space, but you can guess that using a doubling trick. Because if you are fitting too many balls, then you know that basically the metric dimension of the space you're looking at must be bigger than you thought. So you just double your guess for D, and you're still good. And all right, what if if LF is 0? So basically, suppose that actually the deterministic there's a very good fit for a constant classifier. So basically, you can get a very good fit with the Lipschitz function of 0. In this formula, you still get a non-parametric rate because we have this other constant here that keeps the rate even though when this constant is 0. However, by mixing it with an additional classifier with a huge ball, so you can play a little trick and you can get the parametric rate against any f such that you have this the Lipschitz constant is 0. Yeah, what you would really like is to have a scaling of this kind without having this mixed dependency between these two constants, so that basically the rate will gracefully go to 0 whenever you're competing with functions whose Lipschitz constant is smaller and smaller. Well, we don't know how to do that without tuning the algorithm explicitly for a certain Lipschitz constant delta. So we don't know how to do that uniformly over all Lipschitz functions. So this is the best we can get so far. Okay? So, this is a very simple setup. So it's very easy to change it, to play with it, to use it, to implement it. And for instance, one trick we immediately tried, which is very nice, is very natural, is say, okay, let's assume that balls don't shrink at uniform rate, but they shrink with the number of mistakes made by the classifier sitting in each ball. So if a ball makes a lot of mistakes, then we shrink it faster than a ball that makes few mistakes. Okay? This is a way, or this is the picture, this is a way so that the cover will adapt to the local complexity of data source. So now Lipschitz constants are not the best way of measuring this local complexity with something else, but anyway, we also lose the half overlapping property because now balls will overlap with each other, so we cannot use the packing argument anymore. So I don't know how to analyze this algorithm, but this is really working well in practice against this activity recognition data and videos. So we are looking forward to get an analysis of it. So another obvious thing to try is the budget version of the algorithm. So suppose you want to keep the memory of your classifier bounded, so you have actually a constant number of balls with which you can cover the space. So now you would like to kill off balls that are sort of not useful anymore, maybe because the data source has shifted towards a different area, and you want to create new balls, keeping the number of balls constant over time. This is another thing that really works well in practice. We don't know how to analyze it. It's really nice. Okay, so this is what I wanted to say for the first part. Is a little bit of entr'acte with the Cathedral of Toulouse. And now, if you don't have any questions at this point, I'm going to switch to the next topic. Okay, was it too fast? Okay, I'll go slower for the next one. Let's see if we get any questions. Okay, you can think up. Okay, Vianney.
Can you do something if I think everything relies on the fact that L is only between 0 and 1, right?
L is
loss is between 0 and 1.
Yeah.
Can you do something if your loss function is Lipschitz but not bounded in 0 and 1?
You mean the loss is not bounded?
Not necessarily 0 1. Because here you would say
no, you can use like linear classifiers, generic linear classifiers, and then you have a more general version of Lipschitzness. So basically, you have you're competing against the best linear classifier at each single point of the space, but this linear classifier cannot change too much as you move across the space. So that's a different notion of Lipschitzness, but the analysis will carry through completely. So yeah, you can do it. So then you have, you can do regression, so you can have any source of loss you like. So that's not restricted to. I did it with classification because somehow it's a concrete example, it's a sort of points the meaning reading protocol. Okay, I've got at least one question, so I'm allowed to move to the next. You can still ask questions on the previous part. So now we're still looking at online linear prediction, but in a different setting. Now I want to focus on a different problem. I want to be totally parametric now, so non-parametric is gone, but I want to look at a different angle. So let's say we want to look at online. This is called online convex optimization in general. But especially, I'm insisting on the fact that I'm looking at linear predictions. So I again have a completely arbitrary data source, and I'm now looking at the Euclidean spaces. And I have some convex and differentiable loss sequence. Pick your favorite loss. It's just a sequence of losses that are. So these losses may be maybe any kind of loss that depends on labels. I'm just absorbing the labels inside the loss. Okay. So this loss might actually, F1 may refer to label 1 for some regression problem, or anything you like. So the setting, the protocol is similar to before. I'm going to receive the next instance. I'm going to output some prediction PT. Okay, now PT is a linear prediction. It's not a probability anymore. Sorry for the clash of notation. I'm making a linear prediction according to some set of coefficients that the algorithm is cooking up. And then I'm going to pay some loss, which is the corresponding loss in the loss sequence applied to the linear prediction. The loss sequence is deterministic, but unknown. I don't know the loss sequence beforehand. Okay, I don't know the data points beforehand. I don't know the loss sequence beforehand. I just see the next data point. and make a prediction, and I pay the loss. I know what loss I pay, and then what I observe is the gradient of the loss. So the gradient of the loss, I write it in this form. So I define this as the loss as a function of the weights, of the weight vector. And because the prediction is linear, my gradient is going to be just like the derivative of f with respect to the argument times the x, because of the linear part. Okay? Cool. So a lot is known. Again, I'm interested in studying the regret against any fixed set of coefficients, W, so I'm competing against the best linear classifier for the same sequence of losses. Okay? So this is the usual notion of regret. And what we know is that for arbitrary convex losses, without any further assumptions, we know that this regret is going to scale with the square root of time. Okay? It's a nice parametric problem. We get the parametric rate. Yes?
Is it minus the infimum of the value, or is it you just compare to one?
Okay. I don't know the W I'm competing with, but I want to be more specific, more detailed in the regret bound. So I'm not talking. You can take an infimum if you like. Conceptually, it's the same thing. But I'm going to show you bounds for every simultaneously for all W. So yes, I could have taken an infimum. We're gonna look at the class on which the infimum will be taken. So we know that this thing scales with square root of t, and people, this is very well known. If you have some additional assumptions about the convexity, the functions have a certain curvature, you can get faster rates even on arbitrary sequences. If you don't anything, this is the worst case rate, and you're interested of getting the dependence to control the regret in terms of square root of t, and then these parameters. So the W you're competing against, again, this is an oblivious parameter the algorithm doesn't know. The sequence that the algorithm is experiencing, and the sequence of losses that the algorithm is getting. Okay, so this is a very well-known result by Zinkevich, which somehow started the online context optimization view of learning. It says, okay, if you do online gradient descent, you just lead with some chosen learning rate, a nicely chosen learning rate, and you always and suppose that you want. You settle for competing against all linear classifiers W that live in some ball of radius U. Okay, so you always project your predictor down to the ball of radius U because you know you're competing against these guys. Then you can get this kind of scaling. And this tells you that, okay, this simultaneously holds for all W, whose norm, Euclidean norm is of most U, for all sequence of X's, whose Euclidean norm is of most X, and for all sequence of losses, whose derivative is of most G, whenever your prediction, whenever your linear prediction is bounded by C in absolute value. Okay? So you have this kind of scaling that depends on individually on the size of the competitor class, which you have to know because you have to make the prediction, the size of X, which you can sort of guess online, and the shape of the derivative of the loss, which makes sense. If the loss goes up very quickly, then you're going to pay a lot. So this is some scaling that is optimal for the gradient descent. And now, okay, the question is, can you do better than this, under which condition, and so on. So what I want to do is to bring up the following problem. In general, you would like your algorithm to be invariant to data scalings. So when you get the data in practice, you get measurements, you get different measurements. Each measurement will have a different scale. Then you do some sort of normalization. Maybe you do Euclidean normalization. You do L1 over columns, L2 over rows. Well, you don't really know what to do. You try to organize your data in a way that looks nice. But ideally, you would like the algorithm to be independent over linear transformation of your data. Not only scalings. Not only uniform scalings, not only individual scalings of the coordinates, but any arbitrary invertible linear transformation. Okay? So this will give you an algorithm that is robust to any kind of way you represent the data, and it's of course is a nice property to look for. So now a natural comparison class is, of course, is the following. You say, okay, no, I don't want to impose separate constraints on the size of the data points and on the size of the linear predictor I'm competing against. But I will say, okay, I'm competing against all linear predictors whose predictions are bounded by same absolute value. Okay, so this is clearly invariant to, if I scale the data by some linear transformation, I can scale it back. I can take the inverse of the linear transformation of a W, and this will be preserved. So this class is robust to rescaling of the data points, invertible rescalings of the invertible linear transformations of the data points, because the W will scale the data back. So now the problem is, can we design an invariant algorithm that whose regret scales with this parameter C and it has the property to be invariant? So the predictions will be invariant to any linear transformation of the data points, which is invariant. Okay, so this is the question. So, right, so you start, you're immediately led to look at not first order algorithms, which are hopeless in this case, but to second order algorithms, which will have the covariance metrics of the data learned incrementally over time. So let's look at, first of all, let's look at a simpler problem. Let's suppose I get all the points first. So I get all the x's beforehand. I don't know the losses, but I get all the x's beforehand. So now I can say, okay, for those x's, what's the best conditioner of the data? What's the best invertible matrix A, such that if I condition my G, okay, so what is G here? I didn't say what was G before, my fault. G is I call G the gradient. Simple. G gradient. Okay, sorry. G is the gradient. So this is going to make a gradient descent with the conditioner matrix, and it's going to make a projection according to the distance defined by the Euclidean distance defined by matrix A on the class KC. What is KC? KC is the class of all linear predictors that on both that sequence of data will have predictions bounded by C in absolute value. So this is, of course, I have to know all the points beforehand in order to make this projection. So that's why it's called transductive. So now I can apply my online machinery and immediately get, by standard tools, I get a bound on the regret, which holds simultaneously for all W belonging to the KC set, for all the set of W with bounded linear predictions. So now I can look at this bound and reason minimax. I want to pick the best A for the worst case W onto in this set KC. And I can carry this minimax analysis, although I have to cheat a little bit. I'm just enlarging, making the problem a little bit harder. So in order to make this a bit more tractable, I'm looking at a slightly larger set. But anyways, okay, I can pick a best conditioner, which will depend on the entire sequence of data. And that gives me this bound, which you see, you have the scaling, the desired scaling with C, the scaling with the gradient of the loss, which is inevitable, and then you have the scaling with square root of D with the dimension, which pops out in this analysis. So this is not completely minimax. So I did minimax analysis of an upper bound, and then I slightly cheated because I enlarged my comparison class. So I don't know how tight this is. We're working on it. And it is that if we can get a similar bound in a non-transductive setting. So what if you don't know the data sequence in advance? Can you sort of can you still get a bound by building your conditional matrix on the fly? Okay, so we try a standard tool which is called online nucleus step. This is an algorithm that uses this matrix as conditioner, where AT is the identity matrix plus the covariance matrix of covariance gradient matrix. I don't know how to call this. The gradient covariance matrix. Okay, these are the past gradients of the data, of the losses for my predictions. These are some parameters I'm picking up. And so this is it. And then I'm making this projection. Now look at the set. I'm making the projection of the set of such that the W will have a bounded linear prediction on the next data point. How can you do? Well, the next data point I see. No, you remember the setting. I see the point, and then I pick up my prediction. Nothing tells me that WT has to be fixed before seeing XT. Okay? So now I see XT and I say, aha, I saw my XT. I know I have to project onto the set because I want to satisfy this constraint. C is the parameter of the algorithm. Okay, this algorithm is not completely invariant because of this little tiny thing which makes A sub t invertible. Oh, this analysis was okay for whenever this matrix is invertible. If this matrix is not invertible, this doesn't apply. Okay, so in general, I'm building my gradient matrix on the fly. It's not going to be full rank right from the start. Maybe it's not going to never be. It's going to never be full rank. I have to make it. I have to have the identity in order to make it invertible and apply this step. So this identity nails me down to some coordinate system. So the algorithm is not going to be completely invariant with respect to linear transformation of the data. Okay, so, but this is a good start because it's easy. It's something very well known. And it gets me a regret bound, which is very meaningful. It will have this thing here, which is what I pay for being not completely invariant. So this is anchored to the canonical reference system of the data. And then I'm paying what I would like plus a logarithmic term here. So you see, I can kill off this guy here easily because the alpha stays inside the log, but nevertheless it's not. I mean, it's reasonable. It's not totally invariant yet. So the next step would be, how can I get a similar bound with a completely invariant algorithm? What's the idea here? How can I get rid of this identity here? It's easy. Instead of using the inverse, I will use the pseudo-inverse. And right, this is the algorithm. I have the same algorithm, but now I don't have the identity here, and I have the pseudo-inverse there. And now the analysis, you can still do it. You can still apply the previous signature. You have to work more. You have to work more because the math is going to change a little bit. But still you can get a bound. The bound is more complicated. It's not so nice. I mean, this is a sort of a nice form which doesn't take the full advantage of the original bound. And now you see, dependence on the rank of the data metric pops up over here. You still have the logarithmic dependence, and this is the dependence you like, and this is the dependence you don't like. Okay, so again, the actual bound is a little bit nicer than that, and this is a completely scaling linear. This algorithm is completely invariant to any linear transformation of the data. If you linear transform your data sequence, the algorithm is going to do exactly the same. Everything is robust, and this bound is also robust. It's also independent to respect to linear transformation of the data. Nothing depends on the coordinate system you are looking at. So fine, nice. You can get this. This you can discuss whether this is the best possible bound, but you still have a problem here. Okay, this is all very nice. This is all interesting. I didn't do much work. I just put threw at it previous machinery. I did a bit more work to deal with the pseudo inverse. However, if you run second order algorithms, you run into computational problems because you have to keep around these matrices, which are made up by the outer products of the gradient matrices. And these guys are d by t, where t is time, and this guy is d by d. So the least you can do, you have to incrementally update the inverse of this matrix, which you can do in time d squared. You would like faster algorithm in practice. They don't have this d squared dependence where d is greater than action. So you would like algorithms which have a controlled parameter that basically, instead of using a, will use some b. Sorry, this is a. This is not a minus 1, this is a. You would like to get b, and b, instead of using the original matrix of gradients, will use some sketched matrix of those gradients. Where instead of being b times t, is d times m, where n is smaller than d. It's much smaller than b, and that's the parameter of the sketching. So now, by using a standard algebra, you can express the inverse of your sketched data matrix in terms of that. So now, if you want to keep around and update the inverse of this guy, you can keep around h, which is m by m, and then you can do these multiplications, which are d by n. So altogether, you pay d squared for inverting this incrementally. You don't have to do the full inversion, it's just the rank 1 up, it's rank 2 update, so you can do it in d squared. And then m times d to do these multiplications over here. So overall, you get m times d instead of d squared, and m, hopefully, you will choose m small enough so that you can keep with d. So now the idea, okay, what should I pick so that instead of the gradient matrix, I get a sketch? What's a good sketch here? So you go to your old guy, 5 more minutes, which is your online step with projection, and you replace this guy with this other guy, and this is your sketch. And now you can look at the bound you had before for the regret. Now the bound, you can write it out depending on, with the parametric dependence of the sketch. So it's actually very easy. I'm looking at the version with the identity, because the version with the pseudo inverse is a bit more messy. Okay, so right now, how can you control these terms depending on the way you do the sketching? So how do we do the sketching? We know many ways. We know a very nice, people love it here. It's going to be Gaussian random projection. So I'm going to make an outer product of my gradients vector, of my gradients, with a Gaussian vector from normal distribution with a Smith variance. N is the parameter, and then I have, just by simple algebra, I know that basically on an expectation, the difference between my two consecutive sketches is exactly what I want. So it's exactly the outer product of the gradient vector, of the current gradient vector. This is exactly what I want. And I know that my sketch also will be a good spectral approximation of the matrix AT, which is the actual gradient covariance metric I would like to have, that I know with which my algorithm will work. Okay, and n has to be big enough with respect to the rank of the data, the log of time, and epsilon squared, where epsilon is the degree of the approximation. Now, if I have that, in expectation, I can get exactly the same, basically I can get the same amount as before. Because why? Well, this guy's here in expectation is going to be G, and this is exactly, with G, I get exactly the term I had before for this component here. And here I can replace the inverse of B in this norm with the inverse of B with the inverse of A by paying the approximation factor by paying the approximation factor. And this will hold with high probability. And so in expectation, my bound will still be fine, and I will pay MD, I will do M times D work per round. So this is nice and cool. If you don't like randomizing sketches, we can do deterministic sketches. This is a very cool sketching procedure, which is based on a streaming algorithm for item frequency approximation. Has been proposed for doing matrix sketching by Gashami, Liberty, Phillips, and Woodruff in KDD last year. And I don't have much time to tell you this. This is a very simple and nice algorithm. You can use this. So basically it keeps approximate counters for D types of objects, but we only keep M counters where M is more than D. So now, instead of types, you replace types by directions. And then here you get a matrix sketching algorithm. Run. Again, we take your MD times per round. And now you will have a different regret bound, which is deterministic regret, and will depend on the, so now you're doing the deterministic sketching, you're keeping a rank M approximate sketch of your data matrix. So you're going to pay deterministically by how much of the data is beyond the first M eigenvalues. So you look at this thing, which is the sum of the data matrix past of the first M eigenvalues, and you're going to pay in the regretted term, which is exactly proportional to that. The nice thing about this bound is that when M equals D, this goes away, disappears, this you get square root of dt here, so you exactly recover the previous bound. And when the data sequence, when you hit the right time parameter, so your data sequence has a rank which is most M, which is much smaller than D, then you win here. So you actually get a better bound with a better approximation because you have D at the bottom and M is smaller than D. So this is nice, and we have additional results that have to do. I'm leaving 5 minutes for questions. You can get faster rates for X-concave losses. So if you have curvature information about loss sequence, you can get faster rates. Better than you can get logarithmic rates instead of square root of T rates. You can do other sketching, for instance, using Oya's algorithm. You can do sparsity preserved sketching. The algebra becomes a mess, but my co-author Aipeng was patient enough to work it out. And we have experiments running using different kinds of sketches and different data. So this is, I think, is a nice, also a very nice playground in order to get. I think invariance algorithm. I mean, it's a very natural requirement to have for an algorithm. I remember I had an old paper with Gilles talking about all kinds of invariances in prediction with experts, and we started our fixation with the invariances in data already there. And I think this is it's a very reasonable requirement, and being able to match computational efficiency with invariance is also, I think, is a very nice feature of algorithms. Okay, I'm done. Thank you very much for your attention. And, sorry for the input.
Thank you very much, Nicolo. We have just time for one quick question.
Yes.
So I think I don't understand the regret bound with respect to KCT. So
KCT.
Yeah, you remember your function class.
Which one? This one? Or
no, before.
This one? No.
Just before that.
This one?
Yes, here exactly. So you say this is for all W in KCT, but now I don't understand why it's not just for all W, because I can always, on the last round, so let's say I want to compare myself to W, on the last round I'm going to do a virtual feature vector, which is going to be W over the L2 norm of W. And then W verifies, the inner product of W over the L2 norm of W squared is less than 1. So you're saying I can compare myself to this guy. And
wait, but
unless W has to be in KCT for all T or
for all T.
Ah,
for all T, for all T, come on.
Ah, but that's not what is written. Okay. You mean the union?
Oh, I cheated here. Sorry, no, I cheated. No. It's a honest mistake. I wanted to use this notation, and then I used the no, sorry, guys, yes. It's the intersection of that. This is the intersection of those. It's a simultaneous. It was spelled out here. I think it was spelled out here. So it's a notational mistake, yes. It was spelled out here. And this is exactly what the still means. Yeah. No. Otherwise it wouldn't make any sense. I agree with you. Thanks. It's good to have good people in the audience so they can spot you.
And yes. Why are you happy with the dependency on D? Or are you happy with the dependency?
I'm not happy because I don't have a lot of money.
But do you suspect that it should be there? I mean, it's strange.
To the extent that this minimax analysis is true, it should be there. I don't know. I don't want to bet in front of this audience. Maybe privately. Yes. The dependence on D is. I know. It's too fresh. I still have to digest it. Okay. This is unpublished work. It's ongoing, so I want to share. Okay. And the co-authors are people. Well, Seb's colleagues at MSI New York, Alec, John, and Aipeng. Great people to work with there. Okay, thanks.
Thank you very much.